Okay. So for those of you guys who don't know who Zyratex is, Zyratex acquired Cluster last year. That was Peter Brom's new company. We are making significant investments in Lustre, and we are providing some Lustre support services as well. My talk today is on MapReduce and using Lustre with MapReduce. This research was funded by Jim Hoffman at the NRL Naval Research Laboratory. So here's the plan of this talk. So we're going to talk a little about what MapReduce is, and then one of the kind of fundamental tenets of MapReduce, and then compare and contrast the MapReduce running on both HDFS, which is the Hadoop file system, and Lustre. This talk, actually, the research is very kind of theory-based, and then we actually did a little experiment on a kind of a baby cluster to kind of prove out some of the ideas there. All right, so let's just dive right in. So first, I'm going to tell you a little about MapReduce. For those of you guys who don't know, MapReduce is a kind of a two-stage process where you take an input data set, a free-form data set, run it through what's called a map task that produces key value pairs. The reduce task then takes those key value pairs, groups the keys together so that you have a single key and then multiple values, and then the reduce task takes that input and produces an arbitrary output set. So there's actually three kind of I/O phases to this. When you first start with a job, you have to take the job and stick it inside, HDFS generally. You run the map task on that HDFS data set. That's that HDFS bytes read. It might be hard to see this on here, but this upper box says HDFS bytes read. We go through this. That's the map task up at the top. Then between the map task and the reduce task, there's actually a HTTP transfer phase where the data from the output from the map task is sent over to reducer nodes, which typically are on different, can be on a different node than the mapper task. And these are not one-to-one, so you can have multiple map tasks and N map tasks and M reduce tasks, and they don't necessarily have to match up one-to-one. And then the output of that reduce task is then sent out again to a disk. And actually, also let me say that for HDFS, the disk typically is local. So the goal of HDFS is to have the input and the output data on the same node that's actually doing the mapping and reducing tasks. So there have been various other studies using MapReduce and parallel file systems in the background, cluster file systems in the background. So these are all earlier studies. So this is a PVFS comparison with HDFS, and basically the way these generally work is you run your study, you realize that your cluster file systems isn't nearly as good as running HDFS, and you do various improvements to try and make it match HDFS. There's a similar study with GPFS showing the same kind of thing. Oh, well, again, the red over here is HDFS, and they eventually kind of match the performance with various improvements to GPFS as well. The problem with these earlier studies is that there's a fundamental issue that is kind of missing from these things. So the HDFS mantra kind of is moving computation is cheaper than moving data, which that's the basis for trying to run the mapper and reducer nodes on the same nodes that are housing the local data, so the nodes that have the drives. By the way, in case I didn't say this before, and if you don't know, Hadoop generally has a single drive attached, or some number of drives attached to every node in the cluster. So as opposed to a client-server system, it's a distributed storage as well as distributed computation. So again, the idea is to have local storage, and that way they don't have to transfer the data over the network. But the oversight here is that the data is still moved. It's still moved off of a hard drive, and hard drives aren't necessarily any faster than a local network. So if you have a good, InfiniBand, 4x QDR InfiniBand network, you can get data a lot faster than you can off of a local hard drive. So all these previous studies here, the previous Hadoop study, there's been a previous Lustre study, and this GPFS study used the network that HDFS is happy with, which is basically just 1 gig E. So when using these other file systems on 1 gig E, the performance is never very good, basically. So let's look at a specific, theoretical cluster. 100 clients, 100 disks, 80 megabyte per second disks, your standard, whatever, common disk today, and a fast network. So this isn't, outstanding 4x XDR InfiniBand with a gigabyte a second. So with HDFS, you stick that one drive on every client, so 100 clients, 100 disks. On Lustre, you'd stick it in, for instance, 10 OSSs with 10 OSTs, and this is just arbitrary manufactured example here. So this is kind of what that looks like. You have this is both systems kind of together. If we look at it with just as a Lustre system, you wouldn't have the local disks. And then if you look at it as a HDFS system, you wouldn't have the Lustre servers. The thickness of these lines here kind of show the data capacity. So the thin line is 80 megabyte per second, and the thick line is a gigabyte a second. So you can see kind of how the relative rates are kind of showing up in. All right, so if we look at the numbers, so we have 100 terabytes. If we have 1 terabyte disks on 100 clients, our aggregate capacity here on HDFS is the 80 megabytes for every drive times the 100 disks, so that's 8 gigabytes a second. When set up as Lustre client, a Lustre server system, you have your same. So we're having 10 drives, 10 OSTs per OSS. So that's 80 megabytes a second drive times their 10 drives per OSS. So again, that's 800 megabytes for each OSS. And then there's a 1 gigabyte network and an 800 megabyte a second disk availability. So since we can run IB point to point, if we have every OSS serving, say, 10 clients, we can saturate the network with the disk capacity. So we have the exact same capacity and the exact same bandwidth. So the network is not a limiting factor. So that's the exact opposite conclusion of moving compute to data. Moving compute to data is cheaper than moving data to compute. It's actually irrelevant. So that's just all theoretical. And then we have some other advantages as well. So we said that the network doesn't limit the data rate, but the striping now that's available in Lustre actually improves the potential data rate. So for instance, for HDFS, for any one node, the best you can get is 80 megabytes a second. But for Lustre, you can actually stripe that same data across your 10 OSTs, read all the data simultaneously, and get it at 800 megabytes a second. Again, this is, I was saying, we were taking one OSS and delivering all the data to a single client. Obviously, you divide it up, you'll get back down to 80 megabytes, but the point is that for any one node, you can get a much better capacity. So the other thing to note is that a typical MapReduce workload you read data, you compute for a while, and you output data. The compute time is different on every node typically. So what you end up with is that the data doesn't, the I/O portions of the workload don't overlap. So again, you can actually take advantage of that faster I/O throughput to a single node. So this is kind of a graph trying to show what I just said. So the bottom line there is HDFS, where all the nodes are reading for 20 seconds. This is, again, made up numbers. All the nodes are reading for 20 seconds. They're doing some compute time for 60 seconds, and then they're writing all the output for 20 seconds. Well, so since we're getting 10 times faster I/O, theoretically again, we can doing that for 10 Lustre nodes, for instance. We're reading that same 20 seconds worth of data in 2 seconds, doing the compute, and then outputting the data in 2 seconds again. And you can see that the final timeline on this, the bottom line there is we get to shave off 18 seconds worth of I/O time. Okay, and this is all, like I said, just theoretical. This is not measured. So the other big feature of HDFS is that they do replication. So that what they typically do is, by default, all your data is replicated 3 times. So the data is stored on the local drive, and it's stored on a nearby drive for data storage, for safety. And then typically it's supposed to be stored far away as well, in case your data center gets blown up. All right, so, and actually let me throw in here that Facebook just added HDFS RAID, which in practice lowers that 3x replication factor to 2.5 or 2.2, 2.5 storage cost as a trade-off with a little compute time, basically, for computing parity on your compute nodes. So the big disadvantage of doing replication like this is that the replicas are synchronous. So, so for reads, it's fine to have local data and you read it and you just need to read it once. But to write it with 3 times replication, you need to write it 3 times, including 2 network hops. So you're loading up your network with 2 times the data. And you're storing it 3 times, so that's very expensive for writing. HDFS is known as a write once, read many file system, and this is mainly the reason why. You can speed it up by decreasing your replication factor, but then you decrease your replication factor, and your data is not so safe. Of course, you know that the way Lustre generally stores data safely is through RAID. That's a different system. It's a different argument. I think I'm going to get to that later. All right. Data locality. So HDFS, as I said before, reads data on local nodes. It's optimized for that. But it's also optimized. It's not optimized for any particular hardware. It's supposed to be a general purpose system that runs on any hardware, and it's written in Java. It is supposed to not be hardware dependent at all. So what they don't do is network optimization. So it runs just over plain old TCP. There's no direct I/O. There's no DMA. There's no striping. So it's not it's not network optimized. The HDFS data can be read quickly only on the nodes that actually store the data. Lustre, on the other hand, can read the data just as quickly from any node. So you basically remove the data locality requirement if you use a client-server model, a distributed file system model. So what that means is that you now can have an arbitrary number of map tasks. They don't need to map. You don't have to have the same number of map tasks as you have data storage locations. So in other words, if your data happened to originally be stored on 10 nodes, if you're going to run MapReduce with Hadoop, you would probably have to run 10 mapper tasks and not be able to take advantage of potentially the rest of your cluster. If you instead have an arbitrarily fast distribution of that same data, you can run an arbitrary number of mapper tasks. So what that means is, fundamentally, you can have a better cluster utilization. Right? You can use all of your compute nodes to do the I/O and to do the compute task as well. All right. So finally, some actual data. So we actually measured this on a small, like I said, a toy cluster. There's 8 nodes in this cluster with a big OSS and a large network. So what we have here it's probably illegible on there, but in purple, which is on the left, is HDFS on 1 GE network. You can kind of compare that with the red line, which is Lustre on a 1 GE network. You can see that they're fairly equivalent. And actually, the heavy loaded column is actually these two right here, which is the 8 task version of this test. I could probably find this thing here. There we go. Beautiful. Right. So this is basically the 8 node is all of the compute nodes are all running at the same time, all working on the same project. So you can see that the red, which is Lustre 1 GE, and the purple, which is HDFS 1 GE, are pretty much the same. So if you reduce, then we have the next column here is blue, which is a single replication. So this is HDFS with no safety factor. The reads are not affected very much. The writes, you can see actually when we start to heavily load it, the writes speed up because we don't have to send the data over the network again. Green, here we have HDFS which is HDFS running in IP over IB. So again, you get some network improvement there. Again, especially for the reads in the heavily loaded situation, you can get some improvement. The writes are again very expensive. Where are the writes? Writes are very expensive because again we're doing the 3 times replication. So then finally we get to Lustre on on IB on InfiniBand, and you can see that basically the speed improvement is significant, especially in the heavily loaded write case. You can see we're getting here's 104 megabytes a second versus 7.5 megabytes a second on the kind of design HDFS. Bottom line is that hopefully our theory is correct. That the network is with a decent network we can get decent speeds out of this, and we seem to have demonstrated that. Now again, like I said, this is a toy cluster, and if you are going to do this yourself, you should really do a large-scale test first for your particular job. This is test DFS-IO, which is an I/O performance test, Hadoop standard Lustre performance test. We also ran a sort benchmark, just sorting 3.2 gigabytes of data. Again, we have HDFS on 1 GE. This is HDFS on InfiniBand. You can see there's actually, well, relatively little difference there. Again, this has to do with the fact that the reads are pretty much local, so having a fast network doesn't really help HDFS very much. Lustre on 1 GE, basically about the same, on par, and then Lustre on InfiniBand. Huge difference. And actually, this last column is actually quite interesting too. So this is sorting the same amount of data, but instead of on all 8 nodes, all of these are 8 nodes. Instead we're just using 3 nodes for this last column. And the point there is that well, since we saw approximately a 3 times performance improvement, I was going to try to just run this instead of on 8 nodes on a third of those nodes to see what the performance was, and you can still see that it's significantly better than the 8-node HDFS version. And the implication of that is that you can now use a much smaller cluster to do the same job. In other words, you pay for the network here, and you pay for OSSs and MDSs, and you save on compute nodes. Again, this is our small cluster and our particular sort job, so you know, your mileage may vary. We did a little work on tuning Lustre as well to try and kind of optimize it for MapReduce. Oh, actually, sorry, this is not what this slide is about. This slide is about changing MapReduce tuning parameters themselves. This has nothing to do with Lustre. In fact, this is a study on Hadoop from Berkeley. The point of this study is that they modified various things like the mapper to reducer ratio. This is a combiner on and off, changing the spill parameter over here. And the point of this is that they started. This was a tuning study, so they started with at about 1,400. These are seconds, I think, or maybe minutes to run this test. They ended up with half that. So through various parameter tunings, they managed to increase their speed of their job. And this is, like I said, it's MapReduce with HDFS. They managed to double their performance by various tunings. So I just wanted to point out that that all of the work that we had done is on untuned MapReduce. So if you were going to really get into this yourself, you should spend some time trying to understand like how to get the maximize performance of MapReduce as well. And then here's where I was talking about tuning some Lustre parameters as well. So we changed so we have max 30 megabytes here. Next is max read ahead, whole megabytes, and then read ahead megabytes, which is where the whole megabytes is where it starts doing the read ahead. Whole read ahead is the second one is how much read ahead it's doing, and the stripe size. So the one that makes the most difference is increasing the stripe size to 4 megabytes, which a lot of you already know. None of this made a huge difference. We tried. One interesting point was at the end, this column we combined all these different tunings, and we got a measurable write increase, but the effect on read is actually a little bit worse than some of the other potentials anyhow. So depending on your load, you might want to make some of these tunings as well. Data staging. So actually, yeah, unless you're NOAA and do staging to an intermediate file system in the first place, Lustre doesn't generally need data staging. So in other words, the data is already stored in a file system that can be used for post-processing, visualization, etc. So that's why I say this is not a fair comparison. This is the time to copy a 1 gigabyte file from a local hard drive to HDFS from HDFS. So copying it to means that we're doing the 3 times write from HDFS to a local file system to Lustre on InfiniBand and from Lustre. So again, not a fair comparison, both because Lustre theoretically shouldn't really need any staging time. So these numbers should actually be 0. But also this was run on InfiniBand versus 1 gig E. And then finally.